Hello everybody. Hope you can hear us. Can somebody just let us know in the chat just to make sure that the microphone's working? Hopefully it should be. Let me just bring this bit up first. There we are. Hello, brilliant. Somebody said yes, excellent. Okay. Somebody said, how come the timings have changed? So what I've maybe I'm wrong, but the reason why I've changed the timings is that some of the schools have gone back in England for year 10 and 12. So schools and colleges, but I think it's not everybody. So I think about a quarter of the people are going, and they're doing like some kind of rotation. So that's the reason why I've decided to do it a little bit later. If you prefer to do it a little bit earlier, then that's absolutely fine. I just thought it might catch more people if they are at school or college today. But so I'm not going back. Okay, so I just thought that might be the case. If it's not, then we can just revert it back to 1 o'clock. If that's all right then. But what I've done is I've obviously scheduled this video for 4 o'clock, and the question video is also at 4 o'clock. But the question one is obviously on Thursday. So in this video, what we're going to do is we're going to look at year 1 kinetics, because I think that was one of the topics that somebody asked for, and I think what I may do, depending on demand, of course, is I'll do some year 1 and year 2, and I'll kind of alternate between the two for a bit. But at least this one's going to be on year 1 stuff. So if you're in year 12, then you would have done this. If you are in year 11, I know some people are watching these in year 11 and looking into year 1 chemistry. So this will be kind of a new content for you instead of revision. So what I thought was we go through the kinetic stuff. Now, what I would ask you to do as well, so I'm doing it this way, where we're going through content first as kind of like a recap, and then the Thursday's live lesson is going to be on the questions related to this video. So all the questions are all done. So if you click in the comments box below, you can click on the link there, and you'll be able to get a hold of the question sheet, and then you can do the questions on there, and then we'll go through them questions in Thursday's live lesson as well. So this video this lesson, should I say, is going to be all on the content side of it, as it says on there. Okay, right. I'm just going to give people maybe 10 seconds or so just to see if we've got any more people turning up. I've got a slightly different t-shirt on. Got a chemistry one this time. I thought I'd get in the mood at least. Right. Okay, so what I'm going to do is we're going to go through, start and go through the content. Hopefully this should take approximately about an hour. It might take a little bit longer depending on if we've got any questions or anything. As always, what I encourage you to do is to kind of engage in it. So if I go through something and you say, I'm not quite sure what that means, there's going to be some tricky stuff in here. We're going to look at Boltzmann distributions, and we're going to be looking at rates of reaction, catalysts, and practical technique as well in terms of graphs, that side of it. So if you ever get a little bit stuck, just let me know. All right. Right. Okay. So I've got no further questions by the looks of it. So what I'm going to do is I'm going to crack on. We're going to look at the first part. By all means, like I say, chip in if you're not too sure. I've got the chat right in front of us, so I can see everything. Right. Okay. So what we're going to do is we're going to be looking at rate and collision theory first. Okay. So for a reaction to occur, they must collide. You've got to have particles colliding. So this live lesson is all about kinetics, which is rates of reaction. So how fast something happens. So obviously we're going to look at it at a molecular level and work out, how do we actually measure rate, and what is rate, and how do we affect rate. So we're going to look at that bit as well. So particles must collide ultimately, okay, for a reaction to happen. So for rate of reaction, the definition for rate of reaction, what I should say as well, actually, this video is quite generic. There is bits in here which you might not know for each exam board, but I'll point them out if you don't need to know them as best as I can. Try to memorize them. So you all need to know this, whatever exam board you're doing. You need to know the definition. So it's the change in concentration or amount of reactant or product per unit time. Okay, so you need to know that bit. Very important. So the rate can be calculated using this equation. So we've got rate of reactant used or product made, depends what it is, divided by time. Okay, so it's always done in that way. Okay, so for particles, they move all the time, but they collide into each other as well. Most collisions actually don't lead to a reaction, which seems a little bit strange. So just because you get two things colliding, that doesn't mean they might not have enough energy for them to collide and produce it. They might not be in the right orientation, for example. So the vast majority of all collisions that happen, they don't actually lead to a reaction. Okay, so we've got a lot of particles just bouncing off each other in this beaker, and only a small minority of them will actually have enough energy in the right orientation, in the right conditions for them to actually react and produce your product. Okay, so collision theory, very, very important. For a reaction to occur, the particles must collide in the right direction. Okay, that's the first thing, as I said, and they must have the correct amount of energy. In other words, we call this kinetic energy. So the physicists out there, you'll know a lot about this. So kinetic energy is to do with moving, so it's moving energy. So they must have the minimum amount of kinetic energy. So just the minimum amount to allow them to react. If they're a little bit under, there's not enough energy there and they won't react. Okay. So, a nice little introduction there. In terms of rate and collision theory, you need to know your equation because we're going to be calculating rate of reaction later on, and using graphs as well at the same time. So we're going to be looking at a lot of that, but it's just about the theory, the principle behind it, because collision theory is going to be used all the way through this live lesson. Okay, so we've got no questions, so I'm just going to keep going. Right, so activation energy. Okay, it's really important when you're looking at collision theory, or you're looking at kinetics, we need to understand about the energy profile diagrams. Okay, so after each slide, can you tell us before you move on to take screenshots? Okay, yes, I will. Yep, sorry. You can actually. All of these will go onto Allery Chemistry, onto the YouTube channel, so you don't need to worry if you've missed anything. You can always go back. It takes YouTube, I think, about a night to actually render it and whatever they do to it, so it normally pop up in the morning. So if you haven't missed anything, then you can always go back, okay, so it doesn't disappear. Okay, so the minimum amount of energy required for a reaction to occur is called the activation energy. Okay, so this is the minimum amount of energy for a reaction to occur. You might have heard of that if you've done this already. Okay, so an energy profile diagram can show the energy changes in a reaction. So this is an energy diagram of a reaction that's actually happening. Okay, so this is an energy where we've got reactants have a particular amount of energy and products have a particular amount of energy. So in this example here, we've got reactants higher than products. So this means that it's going to be an exothermic reaction. Energy is actually released from this reaction. But you can see this line here, this curved line, is actually showing us the reaction pathway. So which way the reaction is actually going. So initially you need a lot of energy and then it drops back down to produce your products. Okay. So molecules, we have something called bond stretching here. This is just looking at a molecular level. This is brilliant. It's like a molecule disco. So molecule bond stretching, as they have a lot more kinetic energy. So what happens here is the bonds actually start and stretch like this. Okay, so you give them a little bit more energy and they start vibrating a lot more. Okay, like that. And then effectively, once they have enough energy, then they effectively reach the peak, or the peak of the pathway, which is called the activation energy. So this is always between the reactants and the top of the profile. One of the common exam questions, whatever exam board you're sitting, is they'll give you a diagram like this with loads of different letters, and they'll say, where's the activation energy? Activation energy is always between the reactants and the top of the profile. Even if it's the other way around, if it's an endothermic reaction and your products are higher in energy than your reactants, it's still the same. Okay, very important. So make sure you know that. Okay, so at this point, right at the top of that peak, we've got enough energy for them to break. So remember, they've been doing this. Okay, they've been vibrating and vibrating, stretching and contracting like that, these bonds, and eventually they get enough energy and they break apart. And it's at that point, that's your activation energy. Okay, it's the minimum amount of energy required for a reaction to happen. Okay, so reactions that have a low activation energy need a lot less energy to break them bonds. Normally it's heat energy. Okay, and vice versa. Okay, so energy which has a lower one, in other words, if this peak is lower or reduced, you don't need as much energy, like heat energy, to get that reaction to go. So chemists are really interested in this, because if they can make a chemical reaction go, then if they make a chemical reaction go at a lower temperature, that means less energy is needed, so better for the environment, lower cost, etc. Okay, right, so I'm going to move on to the next slide after this, if the person wants to do the screenshot. Okay, right, so Hope everybody's fine with that. I've got no questions in the box, so that's fine. So I'll just kind of move on. Right, okay, so we're now going to look at this strange one. Now this trips up so many people, okay? This is called the Maxwell Boltzmann distribution, okay? So your Maxwell Boltzmann distribution is a way in which, no problem, quick and crazy, right? So it's a way in which we can show the energy of these particles. If we have a box of particles, how much energy does each one of them particles have in that box, okay? So Maxwell Boltzmann just shows it as a graph instead as a chart. So it's a distribution, shows the energy in gas particles, okay? Really, really important. I don't know how some people might find this quite tricky. They might find it quite tough. It doesn't have to be. I think it's about trying to label the diagram and know what the graph means and what the different points mean as well, okay? So particles in a gas sample, they move at different speeds, okay? So it's a bit like having 100 particles in a box. Some of them will move much faster than others. Some of them will have a medium speed. Some of them will barely move at all, okay? They're not all moving at the same speed, okay? So that means they have different amounts of kinetic energy. Not all the particles are moving at the same speed, okay? It's a little bit like, I like to see it as a bit like a motorway. So not all the cars in the motorway are moving at a similar constant speed, okay? Some are going at, well, some going at 60 miles an hour, some will go at 70, and some will break the law and go faster than that, and they'll go 80, okay? So you've all got these cars all at different speeds, okay? But they all have kinetic energy because they're all still moving. So what we're trying to do is we're monitoring how much energy each one of these particles has, and we're drawing it in terms of a diagram, a distribution curve, okay? So if we plot all these different energies on a graph, like I say, we get this Maxwell Boltzmann distribution, which is named after the two chaps who basically came up with this theory. So here it is here. Now this might look familiar. If you've done this in year 1 chemistry, it might look rather familiar. What I'm going to do on this slide is I'm going to go through and walk you through what the Maxwell Boltzmann distribution means, and we're going to label the different parts and work out how it actually works. And actually, some of the questions that I've put together, it is on the Maxwell Boltzmann distribution. There's a question on that as well. So definitely pay attention to this bit. Okay, so the graph always starts, some really key points, must start at 0, 0, must do, always, okay? Can't start it anywhere else in thin air, must start there. So if you're drawing a curve, make sure it draws at 0, 0. With some examples, they give you a mark for this, okay? So it must start at 0, 0. No particles have zero kinetic energy. All particles are moving, okay? Whatever speed they're going, some are moving really slowly, but they do have some kinetic energy. So it must start at 0, 0. The next point is the area under the curve is equal to the total number of molecules. Right, okay, so imagine this, a bit like cars on the motorway. So we have this is basically plotting the speeds of the cars that are on the motorway. So some are going really quick, but not many. Some are going like an average speed, say 60, well, some are going like about 65 miles per hour. So that's most cars travel at that speed. And some will travel a little bit quicker and come up with an average, which we'll come on to in a moment. But we don't have any cars that are not moving, because that's not right. So imagine no cars are broken down, okay? So basically, we've got a profile here, and the area under that tells us the number of particles we have in that box, or the number of cars on the motorway, as the analogy goes, okay? So how do they work out the kinetic energy of each particle? It's a theoretical value, okay? So the calculation is quite tricky, and it's just using an average basically. It's not an exact science. It's really difficult to pick up a particle and say exactly how much energy is. But we take an average and we basically plot that and work out how much product is produced, for example. So it's really complicated. You don't really need to know, thankfully, a lot about it. It's all about measuring on average, what's the likelihood of having particles at the top end with a really high rate of reaction, what's the likelihood of them not, and we can work that out by looking at rate. That's basically how it works, okay? Will they ever ask us to work out the area under the Maxwell Boltzmann? No, I doubt it. If they do, they'll give you a lot of help with it, because you imagine trying to work out an area of a curve is quite difficult. So, okay. When you draw another of these graphs, does the area have to be roughly similar? It depends on, the area has to be the same, yeah, when you draw another one. So if you draw this and you'll have a second curve, which we'll look at as well, the areas must be the same, because that's the number of particles in that box, that the area's got to be the same, okay? Right. Can you please explain the EA and the peak of the curve? I will do. I'm going to go on to that now. Okay. So this middle bit, this is the bit where people get confused with. Okay, and I nearly slipped up myself just before. But the first bit is the peak at the curve is the most likely energy of a particle in a sample. Okay. So imagine you've got a motorway of cars. The most likely speed, if I was to randomly check a car, the most likely speed is going to be, say, 65 miles an hour. So in this case, on this diagram, this is the most likely energy that the particles will have. So if we randomize our sample, we get our box, and I put my hand in that box and pick one out, the likelihood of that being the energy here is going to be quite high. So this is the most likely. It's not the average, okay? Don't fall into that pit, okay? So the next bit is this bit. This is the mean energy the particles have, okay? So this is, if we take all the speeds of the particles, okay, and divide them by the number of particles, we get a mean value. And so this is the mean value here. And the mean value is always to the right, slightly to the right of the peak. It's not the peak, okay? So just be really, really, really careful with that, okay? Because that can be quite tricky. Okay, if you get past that bit, you'll be all right. Okay, there's loads of little pitfalls with this. Right, and to address one of the comments on the chat there, the activation energy is the bit well over onto the right hand side. It's down towards the bottom. So remember, the activation energy is the minimum amount of energy required for this reaction to occur, for a reaction to actually happen. So when the particles collide, they produce a product. Okay, so your activation energy goes there. And these particles right at the far end of the curve, basically these have very little energy, they move slowly. So this is a bit like the slow cars on the motorway, okay? So some are travelling really slowly. The ones in the middle, these are moving with a moderate speed. So these are like 65 miles an hour, let's say. So it's 50 to 65 miles an hour. And then we've got some absolutely blitzing it down the motorway. And these ones are going really, really fast, but there isn't many of these, okay? But in particle terms, this is these have a lot more energy, and in fact, they have more energy, enough energy that when they collide, they react and they produce a product. Okay, so that's really, really important, that part. Okay, so I'm going to move on to the next slide for the person who wants to take the next to take the screenshot. You can do. Why is the most likely energy at the peak? So the most likely energy is at the peak because this is where, imagine that line is like the number of particles, okay? So if we take the number of particles and we record the speed of each particle, we're going to have loads of particles with a speed, or an energy, should I say, of that amount there. So it's a bit like standing on top of a bridge near a motorway and we're recording the speed of all the cars that go by. The majority of them will go at a specific speed that will be probably about the speed limit or just under the speed limit, which will be this point here. So that'll be the majority of them. But the average speed is probably going to be a little bit higher because you're going to have some which will go a little bit faster. Okay. So, and the mean is just to the right. Okay, right. So I'm going to move on to the next one. Brilliant. Okay. So what affects the rate of reaction? So we've brought our peak back in here. Maxwell Boltzmann distribution curve here, and this is where somebody mentioned before about adding an extra line, and this is really important about the area underneath. So you can see here, one of the things which affects rate is temperature. Okay, so temperature affects the rate of reaction, which you might think, okay, that's fine. If you heat something up, it's going to go a lot quicker, isn't it? Because the particles have a lot more kinetic energy, okay, when they're heated. So effectively, we're taking particles, get out the car mode, we're taking particles and we're giving them more energy, so they're going to move around a lot more. So it's like some kind of molecule disco, okay, so they're moving around all over the place because you've given them energy, so now they're starting to bounce around a lot more, and that's going to increase the likelihood of a collision, okay. So a larger proportion of the molecules now will have energy greater than the activation energy, which is that yellow line there, okay, and the red line is showing a new profile of a reaction with a higher temperature. Okay, we're conducting a reaction at a higher temperature. So the larger area under the curve beyond the activation energy. So you can see the area under this bit is going to be larger. We've now got more particles that are beyond the activation energy here. Okay, be careful with the language that you're using though. There is a larger area beyond the activation energy. But the most important thing is the actual energy underneath, the area underneath that red curve is exactly the same as the area under the white curve, okay? And so the main reason why is because we haven't actually put more particles in, we haven't taken any particles out, all we've done is heated these up, okay? Molecule disk, yeah. Right, so key facts, okay? This is on the questions as well if you haven't done this. So when you heat a reaction up, the curve shifts to the right, okay? That's not shifts, I should say shifts. Okay, so the curve shifts to the right. It's further right compared to the other curve. It's lower as well, okay? So we have less particles with this amount of energy here because more of them have got energy over here instead. And the area under the curve beyond the activation energy increases. We've got a larger area, as you can see, under that red curve there, okay? So when we decrease the temperature, we're going to go the other way, okay? A smaller proportion of the molecules will have energy greater than the activation energy. And you can see it there, look. Okay, you've got a much, much smaller area there, okay? But the overall area under all of these peaks are exactly the same, okay? There's no difference in the area, but the area beyond the activation energy does change depending on if you're increasing the temperature, decreasing temperature, or you've got your reference one, which is the white line there. Okay, so the curve in this case, it shifts, that should say it shifts, not shifts, I'll get all that changed. So it shifts to the left, the peak is higher, the area under the graph is the same because, for all of them, the area under the graph is the same because we haven't increased or decreased the number of particles, but the area of the under the curve beyond the activation energy actually decreases. We have less particles with energy greater than the activation energy. Okay, so I'm going to move on to the next slide for the person who wants to take a screenshot of that. I don't know if there's any more questions. Okay, I hope that answers the person's question when they were asking about why is the peak. So I think I missed it. Why is the peak lower? I'm assuming you're talking about the peak for the red one. The peak is lower because we've got to keep the area under the peak to be the same. Okay, so if you take the white one there, that white line, that's got an area under that curve. The red line has got an area as well under that curve, but the areas are actually the same. But with the red line, because we're increasing the temperature, the particles have more kinetic energy, so the area beyond the activation energy has got to be higher because we've got more energy with more particles with energy greater than the activation energy. So therefore, to keep the area the same, the peak's got to be a little bit flatter. It's a bigger area at the end there, as you can see on the end. It's a much bigger area there. But to compensate for that, the peak has to be a little bit flatter here. If it was the same height, that would mean that the red line has got a larger area than the white line, and that can't happen. So remember, the area under the peak is to do with the amount of particles that we have, and we're not increasing or decreasing the amount of particles. What we're doing is just giving the particles more energy or less energy, and so therefore the shape of the curve is actually going to change. Okay? How do you make sure you make the area exactly the same exam? It's just approximate. Okay, so as long as you follow these rules here, these ones in the blue and red box here, as long as you draw a curve that looks like that, then that's fine. Okay, so don't worry, you don't need to measure it. Brilliant, you get it. Fantastic. Okay, right, so let's move on to the next bit. Okay, so why do we get a faster rate of reaction when temperature is increased? Okay, so we've looked at that. We've kind of described it a little bit before as well. But what the examiners are after are specific things. And again, all of this stuff so far is suitable for all exam boards. Okay, so particles move around a lot more at higher temperatures, and they collide more often, and hence the reason why reactions happen faster at higher temperatures. So you can see here, we've got particles there, okay? We're heating them up and they're starting moving around, they're whizzing around in that box quite sporadically, and so therefore they're much more likely to collide into somebody, okay? Will a catalyst change the curve? Yes, we'll come on to catalysts in a moment, okay? Cool, right, so you've got loads of space in that particles, but the combination of more collisions and more energetic collisions means that a small increase in temperature leads to a large increase in rate. You must use that kind of terminology in your exam, otherwise you're going to be stuck, okay? So a combination, forget this, so you've got the combination of more collisions, so you've got a lot more collisions, and them collisions have got more energy, okay, because you've heated them up. That means a small increase in temperature leads to a much, much bigger increase in rate. That's really powerful for chemists because it means that we can only heat it up. Say if we increase it by 5 degrees Celsius, we're going to get a significantly or disproportionate amount of the rate of reaction is going to increase quite dramatically. Okay. Right. Okay. So. Okay. So, whoever's screenshotting this, you can move on to the next slide. I'll move on to the next slide in a moment. But if you've got any questions, like I say, put them in. Okay. Right, so let's have a look at the another thing which affects rate. Obviously temperature does, because the particles are moving around a lot more with more kinetic energy, and they're going to higher likelihood of them colliding and colliding with the right amount of energy. Okay, so we're now going to look at another one, which is concentration and pressure. Now this is more akin to solutions and gases in particular. Okay, similar principle. Okay, remember the collision theory principle. So pressure, increasing the pressure will increase the rate of reaction. Okay, so the particles are closer together, they collide more often, they're more frequent collisions, and a higher chance of a reaction actually happening. Okay, so you can see in the diagram there, we've got a low pressure. The box is effectively, or the effect of increasing pressure is like taking a box. You might try it if you got, if you do it at school or college, if you got a syringe and you push your thumb against the syringe, obviously there's no needle at the end, but you push your thumb at the end of the syringe and you push it, and you can see that by pushing it, you're decreasing the area, or decreasing the volume, sorry, in the syringe, but that increases the pressure. Okay, so effectively these particles that had all this space, now you're squashing them into a smaller space, and that increases the pressure. Okay, so pressure does that. So if you have a reaction that involves gases, then by increasing the pressure, you're going to increase the rate of reaction. Okay, and the other one is concentration. This is more likely to be in solutions, for example. So increasing the concentration will increase the rate of reaction. So the higher the fat, much closer together, they collide more often, there's more frequent collisions, higher chance of reaction. Notice the terminology I'm using is pretty much the same. Okay, it's repetitive, but it's key that you get these words in, because you can get 2 or 3 marks sometimes in the exam, and I think if you understand what this means, it's about the likelihood of something colliding. That's all it is. The crux of it is down to collision theory. So you can see in the diagram here, low concentration, there's not many red dots in there. Higher concentration, you've got more of the red dots in there, less of the blues. So the blues, like the solvent that we've dissolved, are reacting because there's a higher concentration of them than there was in the low concentration. Can you please explain the position of shift in activation energy at the higher temperature? The activation energy is fixed. That doesn't move. It's the curve that actually changes. So if you increase the temperature, you can have more particles with energy greater than that activation energy. Imagine it a bit like a high jump. You've got a bar. Well, it's not. That's a bad example, isn't it? Let's say it is high jump, but the bar doesn't move. Let's imagine it's fixed. So some people will be able to get over that bar quite easily, like an athlete. Somebody like me will have no chance. So I don't have enough physique or energy to get over that bar. Same with particles. Imagine particles have got to have enough energy for them to react. So the bar's fixed, but it's the amount of energy that's changing in the particles. Okay? Okay. Is it working? Somebody says it's stopped. Can somebody say if it's working? Can somebody say if it's working or not? Okay, so this should be coming back on now, hopefully. They're back on, brilliant, excellent. Excellent. Okay. For some reason the software's just decided to, brilliant, okay, software's just decided to stop working, but it's reconnected back again. Okay, so okay, fab, are we okay to continue? Yeah, fine now, excellent. Right, okay, so I don't know where it cut off at, but we're going to move on to the next slide now, because we're looking at pressure and concentration. Okay, it's froze again. Is it working still? It's working now. Brilliant. Okay, right. Okay, right. So I'm going to move on hopefully it should pick up. It's working now. Brilliant. Okay, right. So brilliant. Right. Okay, let's move on. There's gremlins in the works, I think. Right, so let's have a look at what affects rate. Okay, so catalysts also affect rate. Okay, so we mentioned about catalysts before. It's very important because obviously catalysts play a very important role in terms of rate. Okay, so a substance. So a substance that increases the rate of reaction by providing an alternative pathway, and it has a lower activation energy. So the catalyst is chemically unchanged at the end of the reaction. Okay, really important for catalysts. So it provides an alternative pathway for that reaction to happen. It has a lower activation energy. Okay, and the catalyst is chemically unchanged at the end of the reaction. Okay, really, really important that catalysts are never actually used up. Okay, so catalysts are generally used to speed up a specific reaction. So different catalysts are used for different reactions. Okay, so this is where it starts to differentiate a little bit with an exam board. Okay, depending which exam board you're doing. But all exam boards need to know this bit, by the way. Okay, so they're used to make a product faster and can be used to lower the temperature required for a reaction. And so this saves energy and money. So we looked at the activation energy. Okay, so we looked at that bit. So what it does is it lowers the amount of energy required to get that reaction to go. So that's what we mentioned before. Okay, so an example of a catalyst is something called a zeolite, which has got such a fancy name. It has a large surface area, and this is an example of a zeolite here. They're micro pellets. They've got a really large surface area, so it allows a reaction to proceed really, really quickly. Okay, you do need to know about what a catalyst does. An example is zeolite. You might see that mentioned. So I'm going to move on to the next slide. If whoever wants to take the screenshot of it. Okay, right, so types of catalyst. Okay, so let's have a look at the different types of catalysts. So everybody needs to know about heterogeneous catalysts for year one. Some exam boards, AQA, you don't need to know about homogeneous catalysts. And you don't need to know about agricultural products, so used for fertilizers. So manufacture ammonia, and we use a solid iron catalyst to allow this reaction to go. So you can see all of the states here are all gases, but we have iron, which is a catalyst. Okay, which is a solid catalyst. Okay, so there we are. Okay, so increase in the surface area of the heterogeneous catalyst will increase the rate of reaction, and so more particles can react with the catalyst at the same time. Okay. What is AQA? AQA is one of the exam boards, but I think that's what you mean. But if it's not, then AQA is you need to know heterogeneous catalysts in year one. In year two, you might not, if you've done year one chemistry, you might think, what's a homogeneous catalyst? Because that's what we're going to look at now. You won't know that if you're doing AQA, but you will need to know it in year two. So you will need to know eventually all of this. Okay. Right. Okay, I hope it's still working. I assume it is. Okay, so homogeneous. This is basically where a catalyst is just in the same phase as the reactant. So if you do Edexcel, this will be familiar to you. If you do AQA, you'll be thinking, what is a homogeneous catalyst? Like I say, you do need to know this for year two. So generally, homogeneous, if you do OCR as well, I believe OCR, you don't need to know what a homogeneous catalyst is, I think. But eventually, with all exam boards, you need to know it if you're going to do the full A level. Okay. So generally, homogeneous catalysts are aqueous and aqueous reactants. For example, you can use sulfuric acid to make an ester. It's a classic example of a homogeneous. So sulfuric acid is aqueous, so is an ester, so they're both in the same phase. Okay, so the main difference between them is this not an Excel board? It's generic, but it has bits, and essentially, for AQA, OCR, or Edexcel, any of them exam boards, you'll need to know all of this if you're doing the full A level. It's just some exam boards, such as AQA, they kind of slim this down a bit. Edexcel tend to put all of it in year one. OCR somewhere in between. So I've decided to go through all of it because you will need to, everybody, irrespective of the exam board, you'll need to know all of this anyway. Okay. I do OCR A, and you do need to know this for AS. Brilliant. Okay. There you are. So if you do OCR, you do need to know about homogeneous. It's difficult because they'll kind of just slightly tweak it a little bit. So with homogeneous catalysts, they form an intermediate species. They combine with the catalyst, it forms the product, and then the catalyst reformed again. So it's a slightly different mechanism. Okay. Certainly with AQA, you don't do this until year two. I'm not sure with an Edexcel, you definitely do it in year one. OCR, I think you obviously do it as well. Fab. Okay, so let's look at a heterogeneous catalyst. Oops, sorry. Who wanted to take the screenshot of that? If you do that now, because we're going to move on to the next one. Does increase in homogeneous catalyst surface area? No, homogeneous catalyst is when it's in a liquid. So it's not a solid, so you can only increase the surface area of something that's a solid, so that's heterogeneous catalyst. Homogeneous catalyst is a liquid, so there's no surface area. Essentially, homogeneous catalysts are better because they can really kind of intertwine or get amongst the reactants. So homogeneous catalysts are good for that in some sense. Okay, hope that helps there. Right, okay. Okay, so heterogeneous catalysts. So substances absorb to the surface of a solid of a heterogeneous catalyst. So heterogeneous meaning that it's in a different phase to the reactants, okay, in your products. So reactions occur on solid heterogeneous catalysts and they bond with the surface of the catalyst, and we call this adsorption with a D, okay. I believe if you do an AQA you don't need to know this bit, okay. I think OCR you do, and definitely at Excel you will as well, okay. So we call that adsorption. So the bonds in the reactants weaken and break to form radicals, okay. So atoms or molecules which have an unpaired electron, you will have seen that irrespective of what exam board you do, you would know what a radical is. Okay, so radical, you might have seen it where you do reactions of alkanes, for example, use a radical, or CFCs. So you would see that in there. Okay, so and the radicals then react with each other and they make new substances. So a catalyst is a heterogeneous one, is a solid base, and substances stick to it. And I've got some diagrams here to show you in a moment as well. So the new molecules are then released from the surface of the catalyst, and we call that desorption. So it releases from the surface of the catalyst, so it temporarily holds it. Okay. So what we're going to do is we're going to bring back that previous example of the Haber process, where we've got nitrogen plus hydrogen will form ammonia. Okay, so that's your Haber process there. So let's have a look at the catalyst. So here we're going to use a iron catalyst surface. This is confusing. It is a bit tricky, isn't it? Hopefully this diagram might help you. Iron catalyst surface, we've got a solid surface there, okay? And we're going to have nitrogen and hydrogen molecules. What they're going to do is they're going to stick themselves, there we are, onto the catalyst surface. There they are, okay? We call that adsorption, so that all the chemicals, they'll stick to the iron catalyst surface, okay? While it's on that surface, we then have a reaction, because it's kind of bringing them closer together. Normally, these particles will just be floating around all over the place, and the likelihood of them reacting in the perfect orientation with the right amount of energy is going to be really unlikely. So having a catalyst and kind of sticking them on there brings them in close proximity to each other so that they can now react with each other, and that's what the catalyst is doing. So it's bringing them all together. And then what happens is they then break away. So they react with each other, and then once they form all this, they then desorb and they break away, and effectively we formed ammonia. Okay, so that's basically what you need to know. You don't need to know a lot in terms of the actual reactions of them. You just need to know adsorption and desorption. Okay, I'm pretty sure OCR don't have this in year 1. I think they have it in year 2. AQA don't. I think it's for EdXL they do. Okay, so you do need to know this eventually. Right, fine. I'm going to move on to the next slide. Okay. Right, okay. So let's have a look at the energy profile. Now, we do need to know about this. Okay, all exam boards, you need to know about the energy profile of a heterogeneous catalyst. So we're going to bring back that Maxwell Boltzmann distribution, and we're going to look at the energy profile diagram as well. We're going to look at both. Okay. So here, what a catalyst does is it brings forward that activation energy. I think somebody mentioned it before. So that's a bit like taking that bar, the high jump, okay, and you're lowering the high jump. So now, even I can get over that, okay? I literally just step over it. So literally, you've taken the bar, you've reduced it, you've made it easier for somebody to jump over that bar. So a catalyst, in chemical terms, effectively reduces the amount of energy that's needed for this collision to happen, a successful collision. And so therefore, by shifting that kind of line down, we've now got more particles that have enough energy for them to react. So that increases the rate of reaction. Okay? Right, okay, yeah, so it's definitely OCR, it is, yeah, definitely year 2 for OCR. Right, so that's your Maxwell Boltzmann distribution. You need to be able to comment on that. A catalyst moves that activation energy further in, so you've got a bigger area of particles beyond that activation energy. Okay, so energy profile diagram. Let's have a look. Okay, so you can see here that we've got our reactants and products. We've brought that back again. Okay, we've got reactants at the top, products at the bottom, and it's shown as the activation energy with no catalyst added in there whatsoever. Okay, so we've got a fixed energy there. Okay, and then when we add a catalyst, there we are. Okay, the activation energy is then lower. Okay, so the amount of energy required to produce our products, the initial kind of rise, is a lot lower than what it was before. Okay. Okay, so this Maxwell Boltzmann also applies to homogeneous catalysts as well. It's exactly the same. Okay, I hope that makes it a little bit clearer. Okay, I'm going to move on to the next slide for the person who wants to do the screenshot. Okay, it's a bit cold now. Right. Okay. Okay, so I'm going to move on to the homogeneous catalyst. Now, if you're doing AQA OCR, you don't need to know this. Edexcel you do, and I think Salters you do as well, actually. So homogeneous catalysts have a slightly different energy profile diagram. I must emphasise, for AQA and OCR, you do need to know this for year 2. Okay, so you might not have done it now if you're in year 12, but you will need to do it in year 2. So you may as well get a little bit of a head start here. So homogeneous energy profiles, they have 2 activation energies. So remember the heterogeneous, you just lowered that level down a little bit and it was just the same, but just lower. Okay. Here we've got our reactants and products. We've got the same thing. Okay, and you can see we've got our activation energy. This is with no catalyst, so we've got that general rise there. With a homogeneous catalyst, we form an intermediate, so we get this really strange double bump. Okay, so it still lowers the activation energy. You can see that green line is lower than the white line, as you can see there. So it's still done the job of a catalyst, because it is a catalyst, that's why. But this is the activation energy with the catalyst as the first step, as you can see here. So we've got this first rise here, and then we've got an intermediate that's formed here, and then that intermediate then goes on to react further to produce your product. So it forms this kind of intermediate stage there, and you have your second activation energy with a catalyst in the second step. So homogeneous catalysts work in 2 steps. Okay, one of the examples I think you need to know for AQA and OCR is the use of or the manufacture of the contact process, the manufacture of sulfur trioxide. I think that's one of the examples you need to know for year 2. So you do need to know this if you're doing any exam board. Some of them, like Edexcel, you need to know it now in year 1, but later you need to know it in year 2. Okay. Okay, so intermediates are formed at that point. That's that middle point there. That's with a homogeneous catalyst. Oops. Okay, so that's formed in the middle. Right, so I'm going to go on to the next slide for the person who wants to do a screenshot of that. So we're nearly to the end, nearly finished. Okay. Okay, so I don't think there's any questions on that. Right, all exam boards need to know this bit. Okay, so why do we use catalysts? So catalysts are used in industry for the following reasons. Okay, so they lower the temperature needed for reaction to happen. That's good because less money, less CO2. A lot of the time when we're heating a chemical up, we're using fossil fuels to produce the heat to heat the reaction up. So if we're needing less heat, then less fossil fuels burnt. That's cheaper and better for the environment because less carbon dioxide is produced. Speeds up the reaction. So they say in industry, time is money. The quicker you can manufacture something, the better, particularly in these current times where, you know, there's certain chemicals that need to be produced for, tests for COVID-19 and, chemicals to make drugs. You need to make these as quick as you can because there's a time period attached onto it to try and get back to some kind of normality. So that's really important for chemists. And also we change the properties of a product. Now the only exam board that needs to know about this is Edexcel. All the exam boards, not even for year 2, you don't need to know about this. But if you are studying Edexcel, then we use something called a Ziegler-Natta catalyst. And what that can do is turn polyethylene into a more dense, rigid, higher melting point plastic. So if you do an Edexcel, you need to know that point. Everybody else, you can just completely ignore that because it isn't even year 2 for you lot. Okay. And there are environmental benefits, like I say, of using a catalyst. Lower temperatures and pressures are required. It reduces energy and the amount of CO2 produced. And also less waste is produced because catalysts allow scientists to use reactions with better atom economy. So we can, if we're using a particular catalyst, we can maximize the atoms that we're putting in at the start and use them at the end. So instead of using a 5-step reaction, we could do it in 2 steps instead. So that's a lot more efficient. Okay. Okay, brilliant. So we've put, I like the way you link the concepts. It really helps to something in the real world. That's just how my mind works. I think it helps because this is a bit, you don't see this every day, do you? So, right, when are intermediates formed and why? Somebody's put on there, intermediates are formed in homogeneous catalysts because the catalyst itself actually reacts with your reactant and it produces an intermediate molecule, and then it then goes on to produce, then that intermediate then reacts to reform the catalyst back again. It's a different profile. This is year 1 kinetics, so the actual details and intricacies of that are really, for all exam boards, are reserved for year 2. So you don't need to worry about it at this stage, but I will probably, if you want me to, I can do a year 2 kinetics one, and that's where we do go into the, the intermediates that are formed, and how it reacts. Normally it's things like transition metals. You use catalysts, because they have variable oxidation states, so you can form these intermediates. But that stuff is, it might not help. I don't want to bog it down too much in the year 1 stuff with the intermediates, but you do need to know about that in year 2 chemistry, so we'll probably look at that in the year 2 kinetic stuff. Okay, so you're in year 2. So what we'll do, because this video is for year 1 kinetics, what we'll do is we'll probably might look to do a year 2 one if the if people want to do that, then I'm perfectly happy doing that, if that's okay. Right, so why do we use catalysts? Catalysts are also used in cars, catalytic converters, and they're made from a rhodium. This is a heterogeneous catalyst, so it's made from a rhodium, platinum and palladium alloy. Incredibly expensive catalytic converters in cars. The reaction, basically it converts toxic carbon monoxide and nitrogen monoxide, which isn't very good either, and it turns it into less toxic carbon dioxide and nitrogen. Nitrogen gas is fine, it's in the air. And carbon dioxide, the problem with carbon dioxide, it causes global warming. Most scientists agree that it causes global warming, so therefore, releasing this in the atmosphere isn't great on that front. But for directly impacting us, it's safer to breathe in carbon dioxide than carbon monoxide. Okay. What is the year 2 kinetics called in AQA? I think it's just called kinetics. I think it is. I'll have to check that. I'll have a look. I'll have to have a look at the slides. I think it's called rates of reaction or kinetics. It's definitely in there somewhere. So classic example, just to show you where a catalytic converter is, just in case you wanted to know. It's underneath the car. It's in the exhaust. If you're looking under a car, you've got an exhaust and you've got boxes underneath. So it's not the end box. It's the box near the engine. That's where your catalytic converter is. Okay. Do we need to know the catalytic converter reaction? For Edexcel you do, and for AQA you do, for OCR you don't, I believe. But I would just check your specification. Definitely for Edexcel, and I'm pretty sure if it is for AQA, but I think OCR you don't. Okay. Right. Okay. Okay. So we're going to move on to the next one. Okay. Right. So looking at the last sections now. So this is how we can measure rate in experiments. Clearly, rate of reaction is very important in terms of, we're talking about the molecular level and all that. And you might think, well, that's all well and good, but you can't really actually do anything with that per se. We actually need to measure rate by doing a chemical reaction. Okay. And so all of this is the experimental side of it. And all of this is suitable for all exam boards. Okay. You need to know all of this. Okay. So, we can measure the rate of reaction in various different ways. So one of them is measuring how long it takes for a precipitate to form. Now this is fine if the reaction is going to produce a precipitate. So we do this by placing a cross on paper and time how long it takes for this cross to disappear. So in other words, a precipitate to form. Okay. So it's due whole classes around this time always, any schedule. Tuesday and Thursday, most Tuesdays, most Thursdays, there is a week where I'm unavailable to do it, but I always put them on like at the start of the week. So it's Tuesday, Thursday. I've only done it at this time. Normally I do it at 1 o'clock, but I've only done it this time because of the schools. But I think if people will prefer it at 1, then I'll revert it back to 1 if that's fine. Yeah, so But yeah, check out Allery Chemistry, and you get all the updates. If you subscribe, you get all the updates, and it tells you when the live streams are going to be on. It's Tuesday and Thursday, basically. And Tuesdays are content, Thursdays are questions. That's basically how it works. So the problem is with this type of reaction, just go back into this, it's really difficult to know when exactly that cross disappears. And you need to use the same observer. So you look down the conical flask and you basically observe until that cross disappears. Use the same observer and it cuts out any errors. Okay? This time's better. Okay, that's fine. Right, so amount of mass loss is another one. This one, you put it on a top pan balance. So this is great for reactions that produce a gas. So if you're conducting a reaction, you want to measure the rate of reaction it produces a gas, and this is a good way of doing it. So for reactions that produce a gas, you place the reaction on the in a conical flask, put it on the balance, and basically we're measuring the amount of gas that's lost over time. So basically we measure after 1 minute, what's the mass? After 2 minutes, what's the mass? After 3 minutes, what's the mass, etc. Okay, it's a fairly accurate method, but you've got to be careful if the gas is toxic. You don't want to breathe that in. You must do that in a fume cupboard. Okay. Okay, and so the other type of way in which you can measure rate is measuring the volume of a gas. Now you might have done this in school or college where you use a gas syringe. So another way of measuring it, we basically put our substance in a conical flask. This is ideal, clearly, if your product is a gas. It goes up the tube and it goes into the gas syringe, as you can see there. Okay, and what we're doing is we're measuring the amount of gas, well, we're measuring how much gas is produced per unit time. Okay, remember that equation right at the start of the live stream, the live lesson, we looked at the equation. So it's the amount of gas produced per time. So we do it after 1 minute, how much is produced, after 2 minutes, how much is produced, after 3, etc. Okay, and we take all them results, and then what we do is we then need to plot them on a graph. Okay, so okay, somebody said how much do PowerPoint slides cost? If you click on, if you go on to the TES channel, you'll find it. If you go on to, it's the Times Educational Supplement. So you go on to TES, search Allery Chemistry, and you'll see them all in there. I'm not exactly sure what the cost is exactly, but they're pretty good value for money. I know a lot of people who use these slides. These are altered because of the live lesson, but there's ones for specific exam boards. So I know people use these slides to actually print them off and use them as notes. But if you have a look on there on TES, you'll be able to get a hold of them there. Right, okay, so calculating the rate from the graph. So we use them different experiments or them different methods to measure the rate of reaction. So what we're then going to do is take that data that we've collected from our practical, and then we're going to plot them on a graph. Okay, so let's have a look at this graph here. So in this case, we're going to use volume of gas produced. So this is like from a gas syringe. And we're going to do it per time, per unit time. So you can see here that we've got our results here that are plotted on this graph here. Okay, this is a straight line graph. So what we're going to do is we're going to use this to calculate the rate of reaction, how quick this reaction is going. So if it's a straight line graph, it's fairly straightforward. We need to work out the gradient. Now, any mathematicians out there, you might be thinking, well, I've done this before. So gradient is just changing y over changing x. So your y-axis is that way, x-axis is that way. Okay, so it's that divided by that. Okay, so the bigger, there's a lot of dance moves in this video. The bigger the section of graph you use to work out the gradient, the better. Okay, classic rule. When you're always working out a gradient, you need to take as much of that graph as you possibly can because you get a better outcome as a result. So you're going to try and find points as well on the graph where you can actually work out the change of y and x easily. You don't want to be putting it halfway on the line and you're trying to work that out. Okay, so let's have a look. So there's our biggest gradient that I think we can do. Okay, nice suitable gradient. And we need to do the change in x, which is 6 minutes, and the change in y is going to be 4. And so what we do is we put all that into our calculation. So it's 4 divided by 6. Or that's the change there. So it's 4.6 minus 0.6. That's your change in y, and then your change in x. And your gradient should be 0.67. Now the units are centimeters cubed per minute. And the reason why is you just look on your graph. You can see you've got centimeters cubed at the top here, and you've got minutes on the bottom. So your units are derived from the units that you've got in your graph. It's always that per that, whatever it is in your graph. Okay. Okay, so you literally saw this slide in the OCR A Year 13 How Fast video. yeah, you'll find some of this stuff might be in year 2. There's a bit of crossover with kinetics, so it's very confusing with all these different exam boards. Right, okay. So, I'm going to move on to the next slide. For the person who wants to take the screenshot of that. Okay, so just coming on to the last slide. This is the last one. What we're going to do is calculate the... not the last one, it's the second last one, sorry. So we're going to look at calculating the rate of a graph from a curved line instead. So it's the penultimate slide, this one. Okay, so similar type of reaction, except this time we're going to measure the mass of a reaction vessel. So this is a different type of reaction that we're doing, and we've measured the mass of that over time. So the mass is effectively decreased over time. Okay, now with a curve, all we have to do is draw a tangent or a diagonal line that meets the curve at a specific point, and we extend that right across, make it as big as possible, and the gradient is the rate at that particular time. Okay, with a curved graph, you use a gradient. Okay, so engaging, brilliant, thanks. I think I am a little bit hyperactive when it comes to chemistry. So okay, so you've got this graph here. So in this example, we're going to work out the rate of reaction at 3 minutes. Okay, so we're going to pick 3 minutes on that graph, and we're going to draw a tangent right across that. So if you don't do maths at A level, you might think, oh God, we're going back to GCSE now. But if you do A level maths, then you'll think, well, I've seen this before. There's a lot of crossover with maths, to be honest. So your tangent is there, so it just hits at 3 minutes. So there's 3 minutes there, and it literally just hits there, right, nice and flush at 3 minutes. And then we draw our tangent across our curve there. Okay. So the gradient is exactly the same as what we did before, change in y over change in x. Okay, no difference there. So there's our gradient. We've just put our lines in there. There they are. As you can see, they're a bit faint, but you can see them. Okay, so we just put them there. So we're going to work out the change here. So the change in y is 0.8, and the change in x is 4. That's the difference there. We put the numbers in, and we get our gradient of 0.2. The units, again, just look at your graph. Dead easy, grams per minute, okay? Because we've got it in grams here, and it's per minute. So that's how you work out the units of rate, okay? Right, okay, so, okay, I'm going to move on to the final slide for the person who wants to do the screenshot. Okay. Right, so this bit, this one here, you all need to know eventually for year 2 chemistry. For Edexcel, you need to know this in year 1. Oh, lucky you. But I'm going to go through it. I'm going to go through it anyway, okay? Because for the rest of the exam boards, you need to know this for year 2. So initial rate can be found using the gradient of a graph, okay? So you can see we've got another graph here. We've got the same graph that we brought in last time, okay? But the difference is the initial rate is the rate right at the start of the reaction, okay? So right at the start. So just like what we'd seen before, we're going to take the gradient of the tangent, but we're going to do the initial rate. We're going to take it at 0 minutes, okay? So this is, we're going to look at the tangent at 0 minutes. This is quite tricky. It's not an exact science, this bit. But we're basically going to draw the tangent right at 0. So just where it hits there at 0. Okay, so that's our tangent at this point. And the gradient, exactly the same. It's going to be change in y over change in x. Okay, so like I say, if you do OCR or AQA, this is year 2 chemistry. If you do Edexcel, it's year 1. Okay, so if you haven't seen this, then that's fine. Okay, so we're going to take our gradient difference. So we know 1.7 and 1.0, okay, and then we're going to put them into our equation, and we're going to get a gradient of 1.7 grams per minute. Okay, the gradient is the rate of reaction. That's the initial rate of reaction there. Okay, will there be a range of answers for these questions? Yes, there will. Yeah, if you calculate initial rate, to be honest, the exam boards mainly with this one, there's going to have to be a range because you could interpret it and it could be slightly out. But you'll see in year 2 chemistry, initial rates normally used by using what we call ICE tables. Yeah, that's year 2. That's year 2 kinetics. So that's fine. Okay, and that is it. Okay, that's everything for year 1 kinetics. There's a lot of information there. Some of it you do need to know. Obviously, I've pointed out during the video which bits you do and don't need to know, depending on the exam board that you're studying. But that's everything on there. I hope that was helpful. Like I say, this video has gone through all the content that you need to know. There will be a video on Thursday, a live lesson on Thursday, at the same time, at about 4 o'clock ish. So that's going to be the same time. Unless you want it earlier, that's fine. I can nudge it earlier. But have a go at the questions. The questions are in the link. Go in the comment description box below. Click on the link. You'll be able to get the questions there. Have a go at them. We'll go through all the answers on that question there. There's a good mixture of different questions in there as well. And it really gets you thinking about the content on here. But if you ever get stuck with some of the content for the questions, if you ever get stuck in the questions, go back, look at the content. This live stream will be on first thing tomorrow morning. It gets sorted out by YouTube, so you can go and have a look at it on there. It all goes into a live stream folder. I've rejigged the channel a bit, as you may have noticed. But it's still in the live stream, so they all drop into there. So you can go and have a look at it and see if you can try and do the questions on there. All right. Brilliant. Looks though people have obviously found it quite helpful, which is good. So we'll do the questions on Thursday's live lesson, and then, like I say, we'll pick another topic for Thursday's for next week. Sorry, for Tuesday's lesson. All right. Brilliant. If you haven't already, please subscribe to the channel. That'll be absolutely fantastic. It's all for free. So your subscription and your support will be massively helpful. All right, that's it. Okay, I'm going to stop jabbering on. Thank you for your time. And like I say, I hope that was useful. All right, see you later. Bye-bye.